Hi there, this is Ayush from Master Materials today. And in this video, we will master everything about stainless steel. The metal known for its beauty with strength. Now, if you're a mechanical engineer and have been working in industry for a while, you must have used stainless steel, especially the two most popular grades, 304 and 316. In machine design, these grades are commonly used in application where we deal with water, coolant, chemicals or moistures, mainly to resist corrosion. For example, water tank, chemical tanks, piping, heat exchanger. In marine equipments, even complete industrial washing machines are mostly made of stainless steel. We also design fixtures in stainless steel. I have designed many stainless steel fixtures for water leak detection machines, where the components, therefore fixtures, go deep inside water under air pressure for leak testing. Sometimes we also design machines' critical components in stainless steel, simply because in critical components we want to avoid any coating so that we can maintain precision in tolerances. Because if we choose carbon steel or any other steel, we must apply some surface treatment like plating or coating to resist corrosion. And these coatings have uneven thicknesses. They cannot be controlled accurately, and they may peel off with the time. So for better dimensional accuracy and dimensional stability of the critical components, especially in tough environment, we prefer stainless steel. Stainless steel is also a hygienic material. It is non-porous, corrosion resistant, chemically stable, and becomes very smooth surface after polishing. So it is easy to clean and disinfect. This is why in pharmaceutical or food industry machineries, stainless steel are the only choice. Not only few critical components but entire machines in stainless steels. Most importantly, the medical equipments like surgical tools are also made of stainless steel. Apart from that, stainless steel 304 and 316 both are non-magnetic. So they are also used in applications where non-magnetic material is required. For example, in a EV wheel harvester magnet insertion machine, we must use stainless steel, because the mild steel or alloy steel would stick with the magnets during dispensing. Yes, aluminum, brass or other materials can be also used as a non-magnetic materials, but their strength is much lower than a stainless steel. Therefore, for non-magnetic and strength, stainless steel. Now, outside of the machine industry, stainless steels are also widely used for the consumer products, like in kitchenware, in home appliances, like washing machines, dishwashers, refrigerators. Also widely used for architectural structures. Stainless steel 304 and 316 are the perfect engineering materials, but they also have some limitations. First limitation is 304 and 316 cannot be hardened by any heat treatment process. That means stainless steel cannot be used in impact loading or sliding applications where high hardness is required. Second limitation is poor machinability, and there are two reasons for that. First, they are gummy. Due to high nickel content, 304 and 316 produce long continuous chips and require slower cutting speed. Second, they work harden extremely fast. When the cutting tools touches the surface, the metal immediately becomes harder. So the tools has to cut through hardened layer, which increases the tool wear, generates more heat and demands high cutting force. This doesn't happen with carbon steel or most alloy steel. This is why the machining stainless steel is costly as compared to other steel. Third limitation is higher cost. Stainless steel 304 typically costs 3 to 5 times more than carbon steel because 304 and 316 contain chromium and nickel. And especially nickel is very expensive. Also, stainless steels are made with much lower impurities level, which increases the production cost. But what if I tell you that there are stainless steel grades that do not have these limitations? There are stainless steel grades that can be hardened, can reach 50 to 60 HRC, similar to a tool steels. So they can be used as a tool steel in corrosive environment. There are also stainless steel grades that are much cheaper than 304 and 316 and also having better machinability. Also, there are stainless steel grades which are actually magnetic, not because they are impure or having impurities, but they are made in that way. And this might surprise you. The stainless steels 304 or even 316 are not the best corrosion resistance stainless steel. In fact, 304 and 316 are the not best stainless steel in any property, in any area. They are popular just because they offers a mixed balance property. So, as a mechanical engineer, to select the right stainless steel grade, we must understand all the different stainless steel grades, their advantages, limitations, use cases, and availability. And this is what we are going to learn in this video: how to select the right stainless steel grade. Let's start from absolute basic. What is stainless steel? So, the word stainless simply means stain-free. And what is stain? Anything that leaves a colored mark that is hard to remove. In materials, stain mainly refers to rust. So, stainless steel literally means rust-free steel. It doesn't mean stainless steel never rusts, but stainless steel resists corrosion far better than carbon steel or any other alloy steel. Now, what exactly makes stainless steels stainless? The answer is chromium. Stainless steel is an alloy of iron with other elements like carbon, nickel, molybdenum, manganese, and other, just like any other steel. But what's make it stainless is the presence of a minimum of 10.5% chromium. Most stainless steels contain much more than this. For example, stainless steel 304 has around 18 to 20% chromium. So what does chromium do? So the chromium in a steel reacts with oxygen and form a very thin, invisible, passive chromium oxide layer on surface. How thin is this layer? About 1 to 3 nanometer. To give you an idea, that is roughly 100,000 times thinner than a human hair. But even though it's that thin, this passive layer is extremely powerful. Why? Because chromium oxide is very stable. It doesn't dissolve in water, moisture, rain, normal chemicals. So it stops oxygen and water from reaching the iron beneath. And once oxygen cannot reach iron, the oxidation process stops, which means no rust. This protective layer covers the entire surface of a stainless steel. Now, you may wonder, what if a stainless steel surface is removed by machining or scratch or cut? Will it lose the corrosion resistance? So answer is no. If the chromium oxide layer is damaged, the chromium just below the surface reacts with the air again and a new passive chromium oxide layer will form instantly. This self-healing behavior is the biggest reason the stainless steel is so reliable against corrosion. and it's widely used. Now, the stainless steels we commonly used is that 300 series, but they all are one type of stainless steel, one family of stainless steel, but there are four more different families of stainless steel. So let's start with most popular stainless steel family. Austenitic stainless steel, commonly known as 300 series. 304, 316, 310, 321, 316L, and many more. According to 2024 data, austenitic stainless steels account for about 70% of stainless steels usage worldwide. And within this, almost 50% of world's stainless steel's production is only 304. Another 8 to 10% is grade 316. So why so much dominance? Because austenitic stainless steels offers best overall balance of properties. Very good corrosion resistance, good strength, excellent weldability, best permeability, suitable for deep drawing, very high toughness, non-magnetic behavior, and develop a shiny mirror-like finish after polishing. This combination make them go-to material across almost every industry. They are also available globally and they are cost effective as compared to other high performance stainless steels. For general industrial uses, austenitic stainless steel is almost perfect stainless steel family, but they have one clear limitation. They cannot be hardened by heat treatment. And the reason is simple. The grades like 304 and 316 contains less than 0.07% of carbon. To harden a steel through the quenching, the carbon content normally needs to be minimum around 0.3 to 0.4%. Now, about carbon, we also know that the higher carbon gives higher strength, and without carbon, the iron is very soft. This is why the whole reason we add carbon to the iron and create a steel to increase the iron strength. And this brings up an interesting question. That is, if austenitic stainless steels have only 0.07% carbon, then how it's still stronger and harder as compared to regular mild steel, which has actually more carbon, around 0.15 to 0.25%, sometimes 0.5%. There is another question as well. Austenitic stainless steel contain 16 to 20% chromium, some amount of nickel, sometimes molybdenum and other alloys depending on the grade. But even after adding all the alloy elements, around 70% of material is still pure iron. So with this so much iron present, why austenitic stainless steels are non-magnetic? These are the questions that we rarely ask, but these are the questions which separate a designer from an engineer. Knowing the steel grades only by their applications is enough if you just want to choose a material. Anyone can do that. But the mechanical engineering is not only about selecting the things, it's more about understanding the thing. And the foundation of mechanical engineering is understanding of material. So to become a true mechanical engineers, we need to feel the materials, what is inside the material, how it form, how it transform, and why it's behave in a way that look impossible from outside. Because without this depth, every steels will look similar. So before understanding all the stainless steel grades and their use cases, also the comparisons like 304 versus 316, first let's clear the basic that how stainless steels get their strength with almost no carbon. And to understand this clearly, first we need to understand how a regular steels get their strength with carbon because of carbon. And the best way to learn this is through iron carbon phase diagram, the Mona Lisa of material science. So I'm not going to explain through this. I'm going to explain on computer screen. Oops. Hmm. Now, for a moment, ignore the entire diagram and only focus on leftmost vertical line. This left side represents pure iron without any carbon, 0% carbon. At room temperature, the pure iron has a BCC crystal structure called ferrite, also alpha iron. If we increase the temperature above 912 degrees Celsius, this BCC structure transforms into FCC structure called gamma iron, and this FCC phase remains stable up to 1400 degrees Celsius. If we increase the temperature further, the pure iron changes again. The FCC structure reverts back into BCC called delta iron, which then finally melts at 1535 degrees Celsius and becomes liquid, meaning no crystal structure. Now, if we cool down the molten iron very slowly, it will follow the same sequence in reverse. Liquid to BCC, BCC to FCC, and then BCC. This means that at room temperature, pure iron is stable only in BCC crystal structure called ferrite. And the ferrite BCC iron have few slipping system and dislocations that moves very easily. Because of this, the pure iron is very soft. It's ductile and very weak. Magic happens when we add carbon to the pure iron. On this iron carbon phase diagram, the x-axis shows the carbon percentage by weight. Carbon up to 2.06% is called the steel. If the carbon is more than 2.06%, it becomes cast iron. At 6.67% carbon, the materials becomes pure cementite, also known as iron carbide, Fe3C, which is extremely hard and extremely brittle. So on leftmost side of the diagram, we have pure iron, 0% carbon, and on the rightmost side, we have pure iron carbide, 6.67% carbon. So this means this diagram is technically not an iron carbon diagram. It's actually an iron carbide diagram. A true iron carbon diagram would be extended all the way to 100% carbon. On one side pure iron and on other side pure carbon. But after 6.67% of carbon, the stable phase becomes graphite. And under high pressure, the graphite transforms into diamond. These transformations follow completely different behavior, so we study them separately. This is why for the practical reasons, iron carbon diagram is limited to 6.7% carbon. Now, how carbon atoms actually enters into iron? So the starting point of all steels is iron ore. Iron ore is nothing but iron oxide, and it's naturally contain a lot of impurities. So the first step is to remove the impurities. For that, the iron ore is mixed with coke and limestone. The mixture is heated in blast furnace. Coke is a fuel. It provides heat and also acts as reducing agent to pull oxygen out from the iron oxide. Limestone reacts with impurities and form a liquid slag. This slag float on top of molten iron and it's removed easily. When the molten iron settles and cool down, at the bottom we get pig iron. Pig iron has very high carbon, sometimes up to 4%, mainly because the coke, which is basically the carbon, mixes with the iron in blast furnace. Now the pig iron cannot be directly used because it has too much carbon. So the next step is to remove the excessive carbon. For this, the pig iron is melted in a basic oxygen furnace, BOF. Inside the BOF, we blow the oxygen into molten metal. The oxygen reacts with the carbon and remove it as carbon monoxide or carbon dioxide. Now the carbon content drops, and depending on the steel grade we are making, we stop the oxygen flow when carbon reaches the required level. And after this, the molten steel is transferred into ladle. And here we add the alloying elements required for the final grade. Up to this point, all these steps are exactly same for all the steels, even for stainless steel. The difference comes from which alloying elements we added and how much. Now, the steel can be finally solidified. When the molten steel cools down slowly, first around 1500 degrees Celsius, it forms delta iron with a BCC structure. Then around 1400 degrees Celsius is transformed into gamma iron, which has FCC structure. This FCC structure, austenite, is very special because it can dissolve a lot more carbon as compared to ferrite BCC, which is a stable phase of steel at room temperature, which can dissolve only 0.022% of carbon. Now, if you're thinking the iron has been solidified, then how does a solid dissolve another solid? So, this is possible because of interstitial solid solution. Iron atoms are large, carbon atoms are tiny. So the carbon sits in the empty space inside the iron crystal structure. These empty spaces are called interstitial sites. FCC austenite has larger octahedral sites, while BCC ferrite has small tetrahedral sites. This is why FCC austenite absorbs carbon easily, around 100 times better than BCC. But FCC austenite is stable only at high temperature. As the steel cools below 912 degrees Celsius, the FCC crystal starts converting back into BCC ferrite. But the ferrite can hold only 0.022% of carbon. So all the extra carbons must separate out. So where does it go? So it's formed a new phase called cementite, a very hard and very brittle carbon carbide. This cementite increases the hardness and strength of steel. So when cooling is complete, the carbon steel at room temperature is the mixture of ferrite, soft and ductile, and cementite with ferrite called perlite, which is just an alternating layer of ferrite and cementite. So in short, the regular steels get their strength because of carbon. More carbons makes more cementite, as a result more hardness. But if carbon goes above 2%, the amount of cementite becomes so high, make the steel extremely brittle, called cast iron. So in a steel, carbon percent should be always less than 2%. Now let's say if we want to further increase the hardness of a steel. So after steel making, we perform a heat treatment process that's called quenching. In quenching, we heat the steel above 912 degrees Celsius, above recrystallization temperature. Here, steel is not liquid, it stays solid, but its crystal structure is changing. The BCC ferrite converts into FCC austenite, and existing cementite also break down. And as we discussed earlier, the FCC austenite now dissolve much more carbon within. But if we let the steel cool again at very slow rate, then the FCC crystal structure will again start changing back into BCC, and the carbon will come out and again form cementite naturally. And we again back to BCC ferrite plus cementite, nothing changes. But the quenching changes everything. That is, if we cool the BCC austenite steel very fast, at rapid by using water or oil medium, The carbon atoms do not get time to escape from FCC structure. They become trapped inside the FCC. But FCC cannot be remains stable with trapped carbon during rapid cooling. So the structure distorts and changes into BCT, body centered tetragonal. This is a new structure called Martensitic. Because carbon is trapped inside the distorted lattice, the BCT structure creates huge internal stresses. The atomic arrangements becomes extremely rigid. As a result, martensite is very hard and very brittle. This martensite formation is what increases the hardness of steel after quenching. So after quenching, the steel contains some remaining ferrite, some cementite, and significant amount of martensite. Together, these phases gives the steel a much higher hardness than it originally had. A very important point, if you look at the carbon iron phase diagram, you will not see martensite phase anywhere. Why? Because the phase diagram only shows the phases formed under equilibrium condition, meaning slow cooling and gradual temperature changes. Martensite is formed only under non-equilibrium condition, specifically by very rapid cooling. This is why martensite doesn't appear in this diagram. And now let's understand how austenitic stainless steels 304316 are get their strength. So first of all, these stainless steels contains only 0.08% carbon. So with such a small amount of carbon, they cannot form any significant amount of cementite, iron carbide. And also without enough carbon, martensite cannot form. So stainless steel cannot be hardened by quenching as well. That means the strength and hardness of stainless steel is not coming from carbon. It's must coming from somewhere else. And yes, the strengthening mechanism in a stainless steel is completely different from a regular carbon steels. In stainless steel, a very significant amount of nickel is added, and this nickel plays a very important role here. When these stainless steels start solidifying, the higher percent of nickel stabilize the FCC structure. The nickel prevents the FCC austenite from converting back into BCC ferrite. So as a result, austenitic stainless steels remains FCC even at room temperature. Now, FCC is more tightly packed crystal structure as compared to BCC. It has more atoms per unit volume and a more stable arrangement. Because of this, FCC austenite stainless steels have higher strength, higher toughness, better formability, and better ductility, all without depending on carbon. And this is exactly why stainless steels 304316 are more stronger than the mild steels, even though they have almost no carbon. Now let's see that why the stainless steels like 304316 are non-magnetic, while regular carbon steel or any other alloy steels are magnetic. So a metal becomes magnetic only when three things happens all together inside its crystal structure. First, it must have unpaired electrons in its atoms. Second, these unpaired electrons must be able to align in one direction. And third is the crystal structure must allow the formation of magnetic domains. If any one of these three things is missing, the metal behaves as non-magnetic. Iron have 4 unpaired electrons. And in regular carbon steels, the ferrite phase has BCC structure. The BCC crystal structure easily allows the spin of unpaired electrons to align and allow the magnetic domain to form. So BCC ferrite becomes strongly magnetic. But the austenitic stainless steels have FCC structure. And FCC do not allow the magnet domain to form. Even though iron atoms still have unpaired electrons, but the FCC arrangement block their alignment. So metal becomes non-magnetic. That's why 304, 316 do not attract a magnet. Now, if you want to test this concept, take a small piece of carbon steel. At room temperature, it's magnetic because the structure is BCC structure. Now heat the steel around 800-900 degrees Celsius. At this temperature, it's become FCC. And when the structure turns into FCC, the steel loses its magnetism. I hope now this is all clear. And now let's understand the different grades of austenitic stainless steel. So in 300 series we have many grades, but most popular are 304, 316, 321, 310, also 304L, 316L. From these, 304 and 316 are the most common in industry. Let's start with 304, also known as 188 grade. 18% chromium, 8% nickel, or also called as A2. 304 stainless steel is almost 50% of all stainless steels in the world. Having around 18% of chromium give them good corrosion resistance, and 8% of nickel stabilize the austenitic FCC crystal structure as we have seen earlier. And because of FCC, the steel becomes non-magnetic. And also it gives very good permeability, weldability and toughness. Even at very low temperature, below minus 150 degrees Celsius, while mild steel becomes dangerously brittle and poised to fraction at this much low temperature. Now, as in all austenitic stainless steels, including 304, carbon content is very low, below 0.07%. So, austenite stainless steel, including 304, cannot be hardened by the heat treatment. Now, if we ignore the hardenability, in most normal corrosion environment, 304 is our first choice because it keeps the best balance of performance and cost. It's also available in mostly all shapes and size. Sheets mostly comes with 2B finish and also one side mirror polished 8K finish. Now, if 304 is good, then why do we use 316? So 316 have similar chromium, but it has also around 2.2% molybdenum in addition. This molybdenum increases the pitting and crevice corrosion resistance, especially in chloride-rich environment like seawater. Nickel is also slightly higher, around 11.5%, so the weldability and strength improve a bit. But because of the high nickel, cost also increases. So in normal water and atmosphere, 304 is enough. But in marine, chemical, acidic, or salty environment, 316 is better. Strength-wise, both are almost similar. Both grades contain low carbon, but to further improve its weldability and biocompatibility, both grades have also low carbon version 304L and 316L. They contain carbon below 0.03%. So they used in medical implants, surgical wires, bond plates, screws, but for permanent implants, titanium and cobalt chromium alloy are still preferred because they have better wear resistance and long-term biocompatibility. Now, the stainless steel or any other metal are made of many small grains. Where two grains meet, we have a grain boundary, and these boundaries are the most reactive parts of the metal. Now, during welding, the stainless steel can reach around 450 to 850 degrees Celsius. In this range, the chromium in stainless steels react with the carbon and form the chromium carbide at the grain boundaries. Due to this carbide formation, the chromium near the boundary reduces, and when the chromium reduced below 12%, the passive layer of chromium oxide, the film which mainly resists the corrosion, cannot form properly. So the grains remain stronger, but the boundary becomes weak. So the corrosion then starts only along the line and the metal breaks grain by grain. This is called intergranular corrosion. So even a rich chromium stainless steels like 304 or 316, if left untreated, unpolished, or not annealed after the welding or heating, even if surface look clean, the grain boundaries near the weld may already be chromium depleted, and the chances of intergranular attacks are high. So in such conditions where we are not doing any post-treatment or annealing after the welding, it's better to use the stainless steel grade 321 because it has titanium added to it. Titanium has a strong affinity for the carbon than chromium. So when the metal is heated during welding or fabrication, the carbon preferred to form titanium carbide instead of chromium carbide. This means the chromium remains free in steel and stay above the level needed for form the passive chromium oxide layer. No chromium depletion at grain boundaries. As a result, much lower risks of intergranular corrosion. But for very high temperature environment like furnace, 321 is not enough. Where we use 310, which has 25% of chromium and 20% of nickel. So even if carbide form, chromium is still available in excess to maintain the protective oxide layer. So 310 performs excellent at high temperature. It's a scaling resistance at high temperature. So commonly used in furnace, burner, heaters. So if we compare the all Austenitic stainless steels for its main feature, which is corrosion resistance, so 304 is best for normal environment, best price performance. 316 is better for marine, acids, and chloride corrosion. 321 is the best against intergranular corrosion after welding. And 310 is the best for extremely high temperature application. Now, there is one more Austenitic stainless steels which is known for its better machining ability. 303. This has added sulfur which makes the cutting easy. But these inclusions create weak spots. Low corrosion resistance also makes welding very difficult. So 303 is great for machining but bad for welding and prone to corrosion. Now, these Austenitic stainless steels are great for corrosion resistance, but due to very low carbon percentage, these cannot be hardened by the heat treatment. So in application where we need both the corrosion resistance and high hardness, for example, to maintain sharp cutting edge or improve wear resistance in sliding application, then there is a Martensitic stainless steel. These comes under 400 series. There are many grades, but the most common used are 401, 421 and 440C. They contain around 12 to 70% of chromium and they have higher carbon than Austenitic stainless steel. Due to this carbon, after quenching heat treatment, their structures become Martensitic BCT. And because there is no FCC, these grades are magnetic. Also, the nickel content is very low. So they are also cheaper as compared to 304 and 316. And now their grades. So 410 having lowest carbon around 0.15% maximum is general purpose Martensitic stainless steel. 420 carbon increased to 0.15% minimum having higher hardness and strength than 410. And then 440C very high carbon from 0.95 to 1.20%. So this can achieve higher hardness and wear resistance. 410, 420, 431 are mostly used where strength and mechanical performance are needed, like in pump, in valve, shaft, high load moving parts. But 440C is mainly chosen where wear resistance and edge retention are required. For example, the knife blades, ball bearings, plastic injection molds, dies. Now, the corrosion resistance of these Martensitic stainless steels is not good as 304 and 316, but it's still far better than any carbon steel or any other alloy steels. And you can see here, if we compare the SS400, which is a plain carbon steel, it's a Japanese grade, but it's a plain carbon steel having higher corrosion, right? And 440C is better. And then of course 304 and then 316 is even better in same environmental condition after same duration. Now next is ferritic stainless steel, one of the lowest cost stainless steel family, mainly because it's contain no nickel. And since there is no nickel, the FCC structure do not stabilize. So these steels remains in BCC ferrite form, just like regular carbon steel. And because of that, they are magnetic. The ferrite grades contain typically 11 to 18% chromium and very low carbon, usually 0.1%. So they cannot be heat treated by the heat treatment. So you might say that then why do we use the ferritic stainless steel? So the key advantage is higher oxidation resistance at elevated temperature with low cost material. And another benefit is they are easiest to machine among all the stainless steel grade. Their popular grades are 409. They widely used in automotive exhaust system, mufflers, heat shields, and chimney liners. Very economical with basic corrosion protection. 430, better corrosion resistance as compared to 409. Still low cost, common in decorative interiors, kitchen appliances, refrigerator doors, because refrigerator doors should be magnetic. Then the 446 stainless steel, made for high temperature oxidation resistance, used in furnace component, heat exchanger, and thermal equipments. Now we are moving to premium stainless steel, the Duplex stainless steel. These stainless steels combine the best of both stainless steels, the strength of ferritic stainless steel and the corrosion resistance of Austenitic stainless steel. So their crystal structure is 50% FCC and 50% BCC. So we get a balance of toughness, strength, and corrosion resistance in one stainless steel. Duplex stainless steel are more than twice as strong as 304 and 316. And they also provide higher corrosion resistance than 304 316, especially against chlorides and seawater. They typically contain 20 to 28% of chromium, 4 to 8% nickel, and also often molybdenum and nitrogen for extra corrosion performance. However, the Duplex stainless steel are magnetic and also very difficult to machine due to its high strength. So the fabrication needs proper tooling and control parameters. So Duplex stainless steels are typically used where high strength and the corrosion resistance both are needed. For example, high pressure vessels, chemical tanks, and reactors. Situations where thinner wall is required but strength must be remain high. One famous example is Helix Breeze in Singapore is built it using Duplex stainless steel. Now the popular grades are 2205, most widely used Duplex grade, excellent resistance to stress corrosion cracking than 2507, higher strength, and even better corrosion resistance, preferred for more aggressive environment, deep seawater, and heavy chemical exposure. Now, the duplex stainless steels are the excellent in corrosion resistance, but they are not best. There is a grade even beyond the duplex stainless steel for maximum corrosion resistance. This is called 254 SMO, the super Austenitic stainless steel. It's contain very high nickel and molybdenum, which give it exceptional corrosion resistance in all environment, better than all other stainless steel. Their main application is where failure from corrosion is not acceptable, mostly in pharmaceutical processing. And the biggest drawback is, of course, it's very expensive. It's nearly 5 to 6 times than cost of 316. Lastly, the PH stainless steel, Precipitation hardening stainless steel, if I pronounced right. These are unique because they can be hardened by heat treatment using a process called precipitation hardening, where the fine particles form inside the microstructure and increase the strength. The most common grades are 174, 630. They have high strength, good corrosion resistance, and very versatile. They are much lighter. They are much higher strength than 304, 316. They used in aerospace like landing gears, turbine blades, chemical reactors and processing equipments, medical instruments and devices. So this was all about stainless steels, their grade and how to select the right grade as per the requirement, as per the application. And I hope this video will give you a wider perspective on material science. And thank you so much for watching this video.